Atlantic Wall planners wrote the requirement in numbers. Concrete heights, concrete thicknesses, overlap angles, firing arcs. They treated the French coastline as a calculation surface. 10-foot walls and 7-foot thicknesses appeared. Tank width and clearance margins were written beside them. Somewhere in the margin appeared one blunt sentence. Deliver a tank-sized breach without exposing delivery personnel. The Directorate of Miscellaneous Weapons Development received that sentence. Its offices handled problems no normal branch wanted. Staff nicknamed it a place for awkward ideas. Rocket propulsion, unusual fuses, odd guidance schemes accumulated there. The Panjandrum file started as another numbered folder. A clerk wrote the title on a buff cover. Inside, the first sheets reduced destruction to tonnage. The trial notes indicate calculations around 1 long ton. Engineers linked that figure to concrete fracture curves. They assumed brittle failure once impulse exceeded given thresholds. Explosive type, standoff distance, wall reinforcement all entered tables. Underneath, someone circled the figure and underlined it. Carrying that much explosive by hand was dismissed. Landing craft appeared on the next memorandum page. They were already standard items in invasion planning. Their flat bows and ramps suggested a method. Let the craft deliver the charge near shore, then let the charge move itself to target. That phrase, move itself, defined everything that followed. Options arrived as sketches on thin tracing paper. One showed a tracked cart with low profile, another proposed a sled dragged by rockets, and a third sketch placed rockets around a circular frame. The circular sketch gained several arrows and comments. Someone wrote beside it, "Wheels avoid soft sand." The concept hardened into a paired wheel arrangement. 2 large wooden wheels, 10 feet in diameter. Each wheel carried a steel tread for grip. Between them sat a cylindrical steel drum. That drum held the planned explosive filling. This assembly received the name Great Panjandrum. Rockets supplied power instead of any internal engine. Cordite rockets were already familiar to naval experimenters. They bolted brackets around each wheel's outer face. Into each bracket they clamped a solid fuel rocket. All rockets pointed tangentially to spin the wheels. Ignition cables ran back toward the launching craft. Design sheets recorded projected speed and impact momentum. With full load, our planners expected high terminal velocity. They hoped momentum would carry Panjandrum through obstacles. In the notes, guidance occupied only a small paragraph. The projectile was assumed to run largely straight. Symmetrical thrust and good alignment were taken for granted. Manufacture began at a commercial structures workshop. Leytonstone records mention contracts for large wooden wheels. Carpenters laminated planks to reach the diameter. Jigs kept each segment at the prescribed curvature. Steel treads were rolled, drilled, and countersunk for bolts. Fitters hammered them around the circumference on floor trestles. The central drum required heavier fabrication methods. Workers rolled steel plate into a large cylinder. Riveted strengthening rings stiffened the ends and midsection. End plates carried bosses for the main axle. The axle itself was turned on a large lathe. Machinists checked run-out with dial gauges and chalk marks. Rocket brackets demanded repetitive drilling and tapping routines. The shop produced rows of identical steel lugs. Each lug received a clamping arrangement for rocket bodies. Tolerance on clamp diameter allowed for temperature expansion. Trial pieces showed binding when tolerances were too tight. Foreman annotated drawings with revised limits and reissue stamps. Balancing the wheels became an unexpected workshop problem. Cordite rockets were not uniform in mass. Even small mass differences amplified at 10-foot diameter. A mechanic spun a wheel slowly on temporary bearings. He chalked heavy spots as they rotated downward. Workers drilled shallow balance holes behind the tread. Ignition wiring formed another quiet sub-project. Engineers needed near-simultaneous firing across many rockets. They plotted series and parallel combinations in notebooks. Misfires on one side would induce unwanted steering moments. To mitigate, they specified redundant circuits in harness looms. Each loom bore a reference number and inspection stamp. The completed assembly filled most of a small yard. When upright, the wheels towered over nearby sheds. A tarpaulin covered the structure between working sessions. Security notices described it as experimental demolition equipment. Few labourers saw the full set of documents. Most knew only their own drawing numbers and tasks. Transporting Panjandrum to the test site required planning. Height limits on bridges constrained the chosen route. Movement schedules avoided daylight where possible for secrecy. They loaded the device on a low-loader trailer. Chain secured the wheels to welded anchor points. A separate vehicle carried rockets and associated fittings. The chosen proving ground lay at Westward Ho, Devon. The beach offered firm sand and long tidal flats. Nearby holiday housing complicated security arrangements considerably. Trial orders described tests as restricted naval exercises. Warning posters discouraged curious civilians with standard phrasing. Despite this, spectators appeared along dunes and breakwaters. Early tests proceeded with sand filling, not explosives. Trial reports mentioned 4,000 pounds of dried sand. This mass approximated the planned high explosive filling. Engineers wanted realistic inertia without corresponding detonation risk. They measured beach gradients and moisture levels before runs. Rockets were loaded in reduced numbers for initial attempts. Launching involved a landing craft beached bow towards the shore. The device sat inside near the lowered ramp. Ignition cables ran back to a protected firing position. A signal officer coordinated timing with a simple flag. When the signal came, an operator closed the circuit. Rockets ignited with characteristic glare and dense smoke. The first recorded run showed immediate design weaknesses. As Panjandrum rolled down the ramp, thrust fluctuated. Several rockets apparently failed on one wheel side. Asymmetrical torque pushed the structure into an uncontrolled turn. Observers watched it veer away from the notional target. It slowed, toppled sideways, and shed burning components. Engineers returned to notes and added more rockets. They reasoned that additional thrust would reduce exposure time. Higher speed might also smooth over minor terrain irregularities. Workshop orders raised the rocket count by several units. Clamps were inspected for slippage under recoil and vibration. Fuses were trimmed for more consistent ignition delays. Subsequent tests repeated the basic failure pattern. The device accelerated violently, then lost directional stability. Sometimes it turned seaward, sometimes toward the dunes. On one occasion, accounts mention a dog following. The incident entered informal retellings within the department. Official logs restricted themselves to trajectory descriptions and timings. Control features were added after several erratic trials. Designers specified a third stabilizing wheel at the rear. Now, this additional wheel reduced initial tipping tendencies somewhat. However, it introduced new friction and steering complexities. Photographs show a tripod configuration on certain test days. Notes nonetheless record recurring oscillations and sudden heading changes. Steering cables formed the next modification attempt. Steel cables attached to the main wheels via clamps. Operators on the landing craft held the other ends. By tensioning one cable, they hoped to correct drift. In practice, thrust loads exceeded cable and clamp strength. During tests, cables snapped and recoiled across the beach. Each failed run generated more paperwork than distance. Trial forms listed rocket numbers and types for each. Columns tracked misfires, partial burns, and premature separations. And engineers graphed heading deviation against rocket failure percentage. The curves showed no comfortable safety margin emerging. Small asymmetries produced large, unpredictable lateral excursions. The underlying physics remained unforgiving throughout development. Rockets mounted on spinning rims produced complex dynamics. Thrust vectors changed direction as the wheel rotated. Any timing spread between rockets generated transient side forces. Those side forces quickly overwhelmed simple mechanical steering attempts. No practical gyroscopic or fin-based stabilizer ever reached trial. Materials behavior added further variability to every run. Wooden wheels absorbed moisture from the sea air. Their mass distribution shifted between storage and launch. Joints loosened and tightened with repeated stress cycles. And treads deformed slightly under different sand compaction conditions. Engineers noted these problems but lacked easy remedies. Rocket performance itself varied with temperature and handling. Cordite grain cracks produced uneven burn surfaces and thrust. Storage boxes sometimes sat near unheated beach structures. Humidity and salt spray affected external surfaces over days. Ignition lines suffered intermittent contact resistance issues. Combined, these factors multiplied instability in every experiment. Safety officers recorded near misses in separate incident files. Rockets occasionally detached and flew among spectators. Fragments from broken clamps landed near parked vehicles. Burning motors buried themselves in wet sand hollows. On one trial, the device approached the viewing party. Senior officers took cover behind a pebble ridge. No fatalities occurred, but risk calculations shifted steadily. Initial optimism about controllability gave way to caution. Memoranda from safety officers grew more emphatic over time. They highlighted the impossibility of guaranteeing safe trajectories. They stressed civilian presence near the open test beach. They questioned deploying similar hazards on crowded invasion beaches. Training implications appeared in a separate planning annex. Any operational Panjandrum unit required specialist personnel. They needed familiarity with rockets, wiring, and fusing. They also required seamanship to manage landing craft operations. Draft syllabi sketched short courses on handling and maintenance. These syllabi never progressed beyond outline and marginal notes. Handling drills would have involved loading rockets in sequence, as teams would check clamp torque using standard torque wrenches. Fuse lengths would be measured with dedicated calibrated gauges. Ignition circuits would be tested using continuity lamps. Crew positions on the landing craft needed clear markings. Emergency abort procedures required coordinated disconnection and dowsing actions. Logistics officers studied storage requirements for the system. Rockets demanded dry, cool, segregated magazine spaces. The large wheels required sheltered, high-volume covered areas. Transport to embarkation ports needed heavy trailers and escorts. Allocation tables competed with other high-priority assault equipment. Supply branches preferred predictable, proven loads over experimental items. Procurement correspondence shows gradual erosion of institutional enthusiasm. Initial letters carried phrases about urgent, innovative solutions. Later exchanges discussed limited budgets and competing rocket projects. Other DMWD weapons showed clearer results in shorter times. Anti-submarine mortars and rocket parachute devices received emphasis. Panjandrum remained stuck in the experimental category without progress. Engineers continued to propose refinements despite disappointing outcomes. Some suggested fewer but larger rockets for stability. Others advocated flexible mounting frames to absorb impulses. One idea involved adding tail booms with drag vanes. None of these changes advanced beyond rough sketches and notes. Decision-makers grew wary of further expenditure and time. The final major trial brought many observers to Devon. Accounts mentioned service chiefs, scientists, and photographers present. By then, the device carried numerous rockets and modifications. Sand again replaced explosive to limit worst-case consequences. The sequence followed established procedures for loading and ignition. Initially, the machine performed in line with the prediction. Acceleration appeared strong and roughly aligned with intended bearing. Speed increased, spray and sand obscuring lower structures. Then several clamps failed, releasing rockets in multiple directions. Thrust imbalances developed too quickly for any steering correction. Heading shifted towards the position of the observing group. Personnel scattered across the ridge and surrounding wire entanglements. Rockets impacted sand, shallow surf, and nearby shingle. The main structure shed components and lost one wheel. The remaining wheel dragged the drums sideways before disintegrating. A photographic record shows smoke, debris, and disturbed sand patches. Written reports summarized the event in restrained bureaucratic language. Their conclusion addressed safety, reliability, and tactical suitability. After this, Panjandrum effectively ceased to be a contender. No operational establishment requested further development funding. The file accumulated only closing notes and archival references. Some later writers suggested a deception role in planning. Contemporary internal documents rarely support that interpretation clearly. For most involved, it remained simply an abandoned device. From an engineering standpoint, several patterns can be extracted. The requirement prioritized destructive capability and delivery distance. Guidance and stability were treated as secondary constraints. And testing showed that guidance actually dominated overall feasibility. Rockets on wheels formed a system with inherent sensitivity. Small defects produced catastrophic deviations at high speed. The project illustrated limits of incremental modification strategies. Extra rockets increased acceleration, but also increased asymmetry risk. Third wheels improved static balance yet complicated dynamic behavior. Steering cables introduced human input but failed structurally. Each new element created fresh modes of failure and hazard. No underlying simplification of the concept ever appeared. Manufacturing details also informed later rocket work indirectly. Clamping methods for solid fuel motors saw iterative improvement. Tolerance control on ignition wiring improved connector reliability later. And balanced procedures for rotating assemblies informed other projects. Workshops gained experience with large laminated load-bearing wheels. However, these gains were marginal relative to invested effort. Paperwork associated with Panjandrum occupied drawers and archive boxes. Former DM headings recorded dates, locations, and personnel present. Attached diagrams showed trajectories plotted against beach profiles. Handwritten annotations commented on unexpected turns and rollovers. Many pages bore multiple stamps indicating review by departments. The cumulative impression was of orderly, persistent, unsuccessful investigation. Within DMWD culture, the device acquired a quiet reputation. Staff referenced it when assessing later ambitious suggestions. Phrases like inherently unstable appeared more quickly in discussions. The new proposals involving unguided rockets faced stricter questioning. Designers requested dedicated steering studies earlier in concept phases. Experience with Panjandrum shaped that caution in subtle ways. On the invasion beaches themselves, other methods breached defences. Specialised tanks, engineer teams, and conventional explosives acted. None relied on free-running rocket wheels crossing open sand. Historical outcomes left Panjandrum as an unused possibility. Its material components likely became scrap and routine salvage. Its paperwork transitioned from working files to historical collections. In archives, the project now reads as a case study. Initial problem, definition, technical response, and test evidence align. Constraints around manpower, time, and risk are visible. The record shows no conspiracy, and only accumulated practical difficulty. It documents an attempt to mechanize a hazardous manual task. It ends where instability and uncontrolled energy outweighed potential benefit. The Great Panjandrum remains a diagram in many histories. A twin-wheeled frame, a central drum, many rockets. The drawing hides balance weights, clamps, and misaligned bearings. It cannot show misfires, broken cables, and scattered debris. Those details survive instead in notes, photographs, and recollections. Together, they describe a weapon that never left trials. For British weapons development, the file still carries value. It illustrates how requirements cascade through design decisions. It shows what happens when guidance assumptions remain vague. It demonstrates the risk of relying on symmetry under stress. Yet it preserves examples of careful testing around fundamentally unstable structures. In that sense, the Panjandrum fulfilled a quieter function. It did not breach concrete walls on the French coast. It did not roll between incoming fire and mined obstacles. It existed mainly between workshop, trailer, beach, and archive. Engineers measured, bolted, ignited, and then wrote their assessments. Clerks logged each run, updated indexes, and closed folders. The beach weapon stayed on paper as a bounded experiment. Future studies of wartime innovation often return to it, not for spectacle, but for its procedural completeness, a requirement, an unusual concept, disciplined trials, and abandonment. No mythology is necessary to explain that trajectory. The files record enthusiasm, concern, and ultimately administrative finality. The rocket-powered wallbuster remained confined to those controlled documents.